Good afternoon, this is Schweitzer, and this is a quick little video on inter and intramolecular forces. This is something that we want to make sure we are really good at. Identifying the type of bond, which is the intermolecular bond, and then any forces between those particular molecules, if in fact it's a molecule. So, first things first, we got C2H6. We'll just draw, if it's a molecule, we'll draw a little Lewis dot structure or a little structure. This thing has two non-metals, therefore it is covalent. These little dashes stand for covalent bonds. CH3OH, again, all non-metals. This thing is a covalent in nature. Carbon OH, hydrogen, hydrogen, hydrogen. Alright, we got cesium iodide. This is a metal, non-metal. This is ionic. And if you were to draw a structure of this thing, it would just be cation, anion, cation, anion, cation. Just sort of in a bulk crystal. And would go in 3 dimensions, and we would just have a stack of cations, stack of anions in the big pile. So this thing does not have a molecule, therefore it does not have anything between molecules. It just has one force, and that is ionic everywhere. Magnesium is a metal, iodide is a non-metal. So this one is ionic. I skipped one here. Two non-metals. Hydrogen generally is considered to be a metal, even though it's on the upper left-hand corner of the periodic table. We usually treat it bond-wise as a non-metal. Covalent. Alright, like I said, hydrogen generally thought of as a non-metal, and non-metal, that's covalent. Metal, non-metal, ionic, bulk crystal. Non-metal, non-metal. Okay, so I'll draw out the hydrogen quick. It's only one single bond. And then the water looks like this. And then the C5H12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Alright, again, just all non-metals. All non-metals here, covalent. Alright, all non-metals, covalent. Alright, so what about the intermolecular forces? And again, this is just, I would say, just standard information that which you could use to answer a multitude of different questions. We want to know if a particular substance has either our intermolecular types are going to be hydrogen bonding. We got dipole, dipole, and we have London dispersion forces. The first two require a highly electronegative atom, nitrogen, oxygen, and fluorine. And this guy requires essentially everything. Every single atom has London dispersion forces, and we're not going to go a huge talk into it, but essentially factors affecting London dispersion forces are increased number of electrons and long chains, which gives you more surface area. This guy here, we would need to have a highly electronegative atom and to be asymmetrical. Alright, so again, first thing I do is I look for one of these guys. If I don't have it, then I'm going to just fall back to this London dispersion forces. No highly electronegative atom, sometimes I refer to them as Steelers. So it is London dispersion forces. Has a 2-carbon chain, so I'm going to call this even only a small amount of London dispersion forces. This guy right here has a Steeler, highly electronegative atom, so it looks like this guy right here. All right. Again, this guy, this first one, I'm going to go non-polar. Does not have any areas of positive or negative. The ethanol, or so the methanol, has a highly electronegative atom drawing electrons towards it, making this guy partial negative, partial positive. Not only is it polar, it is going to contain hydrogen bonding. All right, nothing for that guy. This guy, HH, has a dipole moment of 0, meaning it has exactly the same electronegativity, equals sharing across the atom, so it's nonpolar. London dispersion forces, and this thing has an extremely small amount of those just because there's very little electrons. Nothing to do here. All right, water. We have a highly electronegative atom drawing electrons towards it, and making this side partial positive, this side partial negative. So we are going to be polar, and we are going to be considered hydrogen bonding. I got a 5-carbon chain, no highly electronegative atom. Electrons will spread evenly throughout this atom. And I have, in this case, covalent bonding. We have, it's non-polar, and London dispersion forces. And I'm going to start saying that this is starting to pick up a little bit more because of our long chain. We likely be a liquid with this chemical. I2 is going to have no stellars, no highly electronegative atom. So electrons are evenly spread out. So it's non-polar. It will, in fact, have London dispersion forces. And this is also fairly high amount because of the number of electrons. Pretty big atom. And then F2 is, again, same atoms. These are both highly electronegative atoms, but the difference in electronegativity is 0. So they cancel each other out and it is nonpolar. And all we have is London dispersion forces, and really not all that much. Alright, so at this point, this question states if two chemicals have the same force, what would be a difference? Alright, well, we'll highlight here at this point, so maybe some ionic compounds. We have, in this case, CSI. I have MgI2, and I have ALP. Well, the biggest thing holding together cations and anions of a bulk crystal is Coulomb's law. Force equals the charge, or the positive charge of negative divided by distance squared. This is a positive 1, minus 1, positive 2, minus 1, positive 3, minus 3. This guy has the largest amount of charge present, and therefore it ramps up the numerator, causing the force of attraction to increase within the molecule. This guy would have the lowest melting point, and this guy would have the highest melting point because of the difference of charge. So difference of charge is a big factor. The other factor involving it is this guy right here, which is radius. If in fact they have the same charge, the smaller ions would be again, a small radius gets them close together, allows them to attract more easily. An example of this might be, let's say, NaF versus NaI. Plus 1, minus 1, plus 1, minus 1. This guy has a much larger radius, which goes up. Therefore, it gets the atom farther and farther away from each other. The nucleus is farther and farther away from each other. So the melting point of this guy will drop somewhat, but not a lot, as opposed to this guy. This guy will be slightly bigger than this one. All right, and then it says, okay, as you look to a list of these chemicals, list 2 that might be solids, liquids, and gases. Okay, so let's go solid, and then liquid, and gas. All right, well, a solid would be anything ionic, and I could just go MgI2 or CSI. A gas would be one thing with almost no intermolecular forces, like H2 or F2. Liquid could be the C5H12. Again, there's some forces, but not that much. And of course, H2O was liquid at room temperature. I don't know. I guess only other thing that you want to keep in mind is what happens, I should say, or what happens, or what breaks when a substance is melted. That is one of our big ideas, and it ends up affecting its melting point. So if you're breaking an intermolecular force, then a very weak intermolecular force like van der Waals, or sorry, London dispersion forces, then the melting point is going to be relatively low, very little energy needed. If you're breaking, let's say, a hydrogen bond, well, then it's going to start increasing a little bit. And if you have to break a ionic bond, then you're going to see a pretty big jump. And if that bond you're breaking is covalent, then it's going to really shoot through the roof. Only time we have that is with a network covalent, like diamond. So the covalent bond is our strongest bond. It just isn't always broken when you melt things. Be very aware of what is actually broken when you melt something. That's a very important concept. Thank you very much.